integrity, but if you go back over life, there are people who make mistakes. It's kind of like what happens with any group of people, like teachers that get involved with, in elementary school, that get involved with their students, and people who, in the Catholic Church, who got involved with their parishioners, and so on and so forth. It happens everywhere. Jerry Sandusky at the university, using his football program to groom young boys. The whole thing is that you have integrity. The key is to be a better person. That being a better person is also, like everything we talk about, a chemical pathway, right? Every time you make that decision to do something positive, that becomes your go-to chemical reaction, even if that reaction costs you energy. Yeah? So what we want to be doing is, instead of giving in to the whatever our negative feeling is, right? And this is all chemical based, right? We're not talking about real emotions. It's not like just, I'm going to choose to be happy. That's not what I'm saying, okay? No one's ever going to diminish how it feels to be in a negative loop, or what you're trying to do to get out of that negative loop. But what I'm saying is that our energy pathways are determined by our repeated behaviors, okay? And that's chemical. You can use more energy to go in a direction or less energy. But whatever pathway you use, you're going to be using that pathway more. That's going to become your primary highway, and you're going to put more of your resources to it. So when we're talking about chemistry, if we have a reaction, right, it starts at low energy and it ends in high energy, right? We're putting energy into the system. That energy has to come from somewhere. It comes from the outside. If we start with high energy and we go to low energy in a reaction, we're going to release energy, and it's going to go to the outside. It doesn't stay contained in that reaction. So whatever we're doing, like today, for example, right? One of the things that helps you with positive mindset, right, is feeling valuable. And what happened? How does that work? How does that cycle work, right? And this is a chemical cycle, right? So for me, one of the things that makes me feel valuable is when I show up and you guys are here, right? That's one thing. However, in order to think I'm imparting value, there also has to come from other outside sources. So today I had an appointment. I had an early appointment, made that, went well. Had a later appointment, and I sat around the office while people who had nothing to do all day, right, who were just there waiting to see someone, got in, did their business, left, and I'm just standing out there waiting. And I had places to go, I had to be here, right? So that in turn could ruin my whole day, right? Because I could say, wow, this doctor doesn't think my time is valuable. But it's really not the doctor's running behind. It's just the way they run that front office, right? And that could be anywhere. It's really not about me at all. It's just I happen to be caught up in what they're doing. So I don't want to let that go, wow, I'm not valuable. Then come in here and go, oh, wow, I'm not valuable. What I'm doing is not valuable because society's not honoring it. It doesn't matter what society does. It matters that you think you're valuable. So I have to come up with a pathway for that. Yeah, I did, of course, because in my mind, the world really is about me. So let's get started with, did that answer your question?
Yeah, that was a long version.
Right, so in my world, in the scientific world, in the PhD world, right, when you go to talk to someone about science, you talk and you create discussion points, and then they talk and talk and talk. And sometimes you just zone out and fall asleep, and that's quite all right too. And the things I put on the podium yesterday aren't here. I went through all the trouble putting them on here. Okay, hold on. Any more questions about reports and when they're due and things like that? Any questions on the homework? Did anybody get those last three problems?
We're going to switch to the back after class.
You already did, Nate?
When the homework was due today?
Yeah. Do you want to put one of the last ones on the board? I'd appreciate that.
I actually had to ask one of the anesthesiologists that I work for, and he actually wrote it all out for me. Yeah.
Nice. Do you wanna put that on the board?
Well, I think I took a picture. I don't think I brought it with me, the piece of paper.
Oh.
But you took a picture?
I think so, but then I'd have to stop.
Oh, right, 'cause it's on your phone. Yeah, any one of those.
Yeah, it's like,
Right, so Nate's gonna give you one more.
Oh, wow.
it was crazy.
That's awesome.
That is due today at the end of class or at the end of the night?
I already turned it in.
But that's all right, you can resubmit. I mean, you should see it one way or the other, because what am I likely to do? What ones that are hard to do, you might wanna see them again.
I couldn't even ask Google this one. I went on Chem.
Chegg didn't even have it?
Chegg
What,
didn't
they
have it.
slip it.
I
better-
dropped in for a tutor. Nothing.
Okay.
There was one website that pulled it up, but it wanted me to pay for the answer. And I was like, no thanks.
No thanks, not doing that.
Not today.
And of course, after saying all that, I don't have a single calculator with me in my box of calculators,
Oh.
not in the trunk, don't have one in the backpack, I'm so.
That's okay.
But that's the way I'm going.
That's okay.
I left all mine at work too with my notes.
Burn it up.
That paper.
That's gonna be good.
Cause I ran out of
Yeah.
it.
So it's a good sign.
I have one on my phone I can use, but like for, exams and stuff, I need one.
Anyone else do one of those last three problems that wanna put it on the board?
So when he showed me today, he was turning, he was telling me how like the 10 to the negative, is it 34 it says? He ended up changing them all to positives. So it was interesting kind of the way he.
You mean like, so you put them on the bottom?
Yes, he put them all
So
on
he
the
switched
bottom.
them?
Yeah, he switched everything and brought it all down.
You can do that, right? Because what is, yeah, you can manipulate exponents in that manner, yes.
I tried to remember the last one.
You wanna try it?
Yeah.
This is not good either. What's going on here? Okay.
Today. Without a W or just for a reason?
It's about a W today.
Really? They really shortened that.
I wonder if you can look it up.
Look at them. We can actually, on our syllabus?
Oh. So for the math problems that are on the homework, we don't have to show the work, we can just write it out like that and put the answer
I don't know what you mean.
on A, his example for A.
Well, yeah, cause it's all calculator work. I don't know what other work you'd want,
Oh,
right? It just,
where's Dom? We don't have to write the whole problem out.
I did.
what do you mean, right? I don't know what you mean.
Like work, do you show the work?
Well, yeah, that is showing the work, right?
Yeah.
I mean, for me, it is, what else could you do?
I don't know, you know, like on a multiplication problem, it's like, you're gonna have to break down and write it all.
Oh, you mean, so like.
Like
just-
if you didn't have a
So if you
calculator.
did, so what you're saying is, you do these two.
Showed every step.
Step, and then you do the next step.
Yes.
No, you don't have to do that.
Wonderful.
As long as you can put it in the calculator, right?
Awesome.
Yeah, now there are other problems where you have to show everything, but like when we get to writing out, net ionic equations and ionic equations,
Well, that
and you
makes
do wanna,
sense.
you do want to, like Jules is doing here, you wanna make sure you, do your manipulation of the formula, I wanna see that. So I know how you got from A to B, but as far as plugging it in the calculator, and I would say, the key to remembering how to do exponents on a calculator is to always put every exponential number in a brackets. Which is really more a math thing than a chemistry thing. Except unless you were a physical chemist. Okay. That is interesting. We're on the 7 here. Maybe I should have canceled class and stayed at the cardiologist. Oh well. Maybe next year.
Your health is more important
Not really.
than us.
My blood pressure was going up waiting in there though, which might cause an event, you know?
Yeah. But you're in the doctor's office, and they have all the stuff
Nice
there.
place to.
Yeah, let's have an uneventful day in class though. Please.
We're going to, go on. It's always uneventful in here. Let's see. Oh good, I have the bio lectures. Where are my lectures? All right, what problem, what number was that?
1.66.
Hold on, thank you. Does that make sense? 34 plus 8 minus 24 plus 9. 23. Uh-oh. Oh, a bunch of numbers. Right, so to get, for these problems, to see if they're anywhere near, you take minus 34 plus 8 plus 9. And so, because that's the exponents here. And so as long as you're in the ballpark, as long as this comes out somewhere around 34 plus 17 is around minus 17, and then you figure in, there's some other things going on here. So 19's in the ballpark. This one's 23 plus 3, so about 20, or 2, so about 24, that makes sense, 23, 5, yeah, right in there, so perfect. And then what do we have here? We're just changing, good, and then mass and volume. What would I want here? I mean, we have the final label, but along the way, we want our other labels. Okay? Good work, thank you, both of you. Feeling very whimsical on that. That's pretty selective. Well, let's see. Okay, well, might have to go back to, oh, it's posted, huh? The lecture's posted, right? Yes. Say yes.
There should be the lecture that you posted from Tuesday's class. on there.
Right, it was supposed to be given Tuesday, but I'm a day behind already. Right.
I think it's on there, I have it printed.
You didn't print it out. Where are we? Oh, my God, we're using up a lot of time. All right. Watch this thing. Good thing I had my review last semester. Holy cow. All right, that's why I was waiting for Nate to get here. Never start till Nate gets here. Modules, so I don't know where anything is. one. There we go. And let's blow it up. Okay, so we won't have a fancy PowerPoint today. That's okay. This is like when a comedian bumps. This is bad. All right. So we have homework 2 passed out. We have chapter 3 reading quiz, which is called reading quiz 2. And, oh yeah, I wanted to go over that. So the idea is that when we do homework or we do reading quizzes, we do them on a separate sheet of paper, right? And I was gonna write this all on the board. So we're gonna do a reading quiz with a separate sheet of paper. Or if you do it on your computer, you can just put the question and then answer it, and then put the question and then answer it. But if you do it by hand, you don't have to write the question, but please be sure to write the numbers that correlates to the question if you're doing it on a separate sheet of paper by hand. And a lot of people are now doing that on their computers and just turning it into PDF that way, which is fine. I love that. The less paper, the better, right? Also with homework, do the homework on a separate sheet of paper. And again, the questions are not multiple choice. They are each A, B, and C, and D is one of the problems to do. So that also needs to be done on a separate sheet of paper. And in interest of knowing what goes with what, go ahead and put your name on each sheet of paper, just like it's old days. There we go. So when we measure things, right? We've gotten into measuring. We're doing a measuring lab right now, right? And today we're going to be measuring some salts. So an unknown salt, and we're going to try to figure it out based on density. So a runner eats breakfast around 9 a.m. Around 1 p.m. We already talked about this slide, didn't we? The runner sprints 100 meters in a time of 9.7 seconds. How much time has elapsed between breakfast and crossing the finish line?
So,
4 hours and 9.79 seconds.
There you go, right? The total time, right? The total time. Which wouldn't really be that good for us, would it? Right? Because we're really looking for how fast did he run the 100 meters, not, how long did it take. But it gives you an idea why you need, we go from 4 hours to 9.79 seconds. There's a huge difference in the certainty or uncertainty, right? The 9.79 seconds is almost insignificant in the measurement because we're measuring from 9 to 1, right? So really you could forget all about how fast he ran it if you're just interested in his day. But if you're interested in that part of the day, now all of a sudden the other two measurements don't really help you, the 9 a.m. and the 1 p.m. You see how that works? Right, so when we're trying to measure something, we need our measurements to be the same. And so we probably convert these to seconds, right? That would be one way of doing it, but it's still the seconds of those 4 hours, which would be 240 seconds, be 240 minutes, and then times 60 again, right? Now that's also going to dwarf the 9.79 seconds. So what we want to be able to do is be precise and accurate, and that problem does not lend to that. So what is precision? Precision is when we do something reproducible, right? How close to the repeated measurements they are to each other. So if I measure something 10 times, and this is what we just did in lab, right? We filled that little cup with water, and we're trying to get it very close each time, but we didn't, did we? Because there was a flaw in the system, all right? accuracy is how close the measurement is to the true value. And also we failed there, right? Because our cone was which way is it? Convex, concave, which way is it? Concave, right? So you want, at the point we were measuring, part of it was sticking out of the water. We weren't getting an accurate measurement, so we weren't very accurate either. So that would be what we call a systematic error. It's part of everybody's measurement. You all had the same error, right? Because when we cut our cone, it wasn't level. And we know that going in. So everybody's error is gonna be the same, maybe not the same amount, but it's the same type of error, and that goes with the system that we're looking at. Then random error, our measured values should be both higher and lower. So in a systematic error, all the values are either higher and lower. So in our systematic error, they're all gonna be lower because we had part of the cone that wasn't underwater, right? So everybody's values are gonna be lower than what they are. And then when we did the measurement, we found that to be true, right? Our measured value before we did and calculated value was much greater than the filling with water value, right? In general, right? Yeah, okay. So a random error would be how much leaked out in between each use, right? Because sometimes it could be higher, sometimes it could be lower. It's gonna be different every time. So, and it doesn't belong to the system. It's something we do normally. Like we don't read the burette accurately or precisely, right? We get an upward angle reading the burette, and so one time it's high, and the next time we read it, we have a downward angle, and then it's low. And here again, here's the bullseye analogy that's everywhere from the time we like in 7th grade. Accurate and precise, everything's right in the bullseye. Precise, everything's grouped together but not quite in the bullseye. And then not very accurate, not very precise. I like to put them all over the place when that happens, but compared to the 3 that are right in the center, not accurate or precise. So let's weigh a 10 gram sample multiple times. In trial 1, we get 10.49 grams. Student B gets 9.78 grams. Student C gets 10.03 grams. So the same student is going to do 4 trials. And in trial A, student gets 10.49, then 9.79, then 9.92, then 10.31. And what happens there, right? We're taking all these measurements and they're kind of all over the place. Some are high, some are low, right? What tells us that that's what kind of error? Here's the actual value. Some are high, some are low. So if we go back to that, that's what kind of error? Random error. Yeah, there you go. Now this student right here, B, he gets 9.78, 9.82, 9.75, 9.80, and there's the average, and here's the true mass in blue. And all those measurements are below, so that's what kind of error? Systematic error, right? Because they're all on the same. And then C here, he's like really close, right? A little bit high, a little bit low, a little bit high, a little bit low. So it has a very small random error. He's minimized his random error. And he's very accurate. So he's very accurate, very precise. This guy's very precise, not quite so accurate. This guy's neither one, right? They're just not really paying attention. And so your numbers will show you who's paying attention and who isn't. So in last night's lab, I had a bunch of people doing the same experiment, right? We have 7 people in the lab. And they're pretty much on their own because that's what you're supposed to be doing. You're supposed to be making your own observations, and then if you get stuck, you talk to me. So one person they were collecting ethanol samples from 70 to 80 and 80 to 90 and 90 to 100. And one of them nailed each step because went very slowly, was very interested in the process, didn't get fancy by turning up the heat or anything. So systematically, he was level and he was trying to minimize his random error. Other people, they just went and cranked their thing up and all of a sudden their temperature jumped from 70 to 100 and everything they collected was all in one fraction, which isn't so good, right? That's not what you want. But again, it's a learning experience. You don't know that's gonna happen, maybe. And so you do it and then you're like, oh no, what do I do? Well, the next time you do an experiment, you slow down and you follow instructions. But at the same time, you have to make that mistake in order to get there. And when you see this kind of thing going on, you think, oh, it'd be really nice if this person slowed down. And that's kind of the gauge of what we're looking for as you move forward into the higher levels, right? You don't, as people move up, you don't want to give this person, because it could be, I mean, I don't want to be mean to men, but this person could someday be doing a very dangerous reaction, and basically if I'm the supervisor, I'm not going to allow them to have that opportunity where this person didn't notice there was a big error, and this person is very fastidious. So the more dangerous and complex it is, the more likely it will be assigned to this person. Yeah? This person's good, would be my second choice, but what's going on here? Right? Okay. So atmospheric carbon dioxide, big talking point these days, right? How much CO2 is in the air? Is it the right amount? Has it ever been this high before? Do we have samples from before we were born, dinosaur samples in the ice? But once we started measuring, 1960, at this location in Mauna Loa, right next to a volcano, it's increased quite a bit, right? From 300, 320 about, somewhere there, 315, all the way up to 390, which seems like a huge increase. But you're doing parts per million, right? So parts per million, if we remember, a million is this. So, right? That's 1 part in a million. This is 320, and going to 390, which means that much change. Which, when we started doing this, was really beyond the detection limit. But now our instruments are much more precise. It's not saying that this much change isn't large, but it could easily be insignificant in a measurement, but it also might be very significant. We have no way of knowing because we didn't create the system. But we need to monitor it and be aware of it and have discussions on it and have people that, you know, come up with one idea like this is going to ruin humanity as we know it, compared to the other people who say, no, we don't know enough yet, and they temper each other, right? Because you have the people on the extremes, one, that's the end of life, and the other is going, it doesn't mean anything. And the reality is, it's a change, and it's obviously due to mankind, and what's the significance over time, and how do we balance these two end of the world and nothing happening at all kind of arguments. And that's why committees are so useful, because it's hard to get anything through a committee, and if you have enough people on that committee, you have enough opinions that things move very slowly, so you don't rush to the conclusion the world's ending, or that it's no big deal at all. So that's one of the other benefits of science. One of the things that happened here with these measurements is, right? You need to take a lot of data. So in 1960, we were only measuring in one spot in the whole world, Mauna Loa, right? So any data from that era is just from one spot. We don't know what was going on CO2 of the rest of the world, right? And then we came up with a way of, due to advances, right, we have questions about dissolved CO2 in the water and how much, based on how much is dissolved in the water, how much is frozen in these core samples, and then, so we thought I had a theory about that too. Turned out it was wrong. But it was a good theory while it lasted, and it needs to be explored. All theories need to be explored, and that's why people constantly invest in science. And that's why when we get back to integrity of measurement and integrity of answering questions, it makes a difference, right? If people that are doing it have integrity. So, anyway, why were we doing that? You have to have a lot of examples. And then you also have to figure in what happens in an annual cycle, right? So if you're taking the measurements here during the uptime and not during the downtime, now you have a whole different series of measurements. But you won't know that until you have a whole series of measurements, which is why when we're reacting to what we're reacting to now, one day we have this and the next day we have that. It's not because people don't know what they're doing, it's just because we don't have enough data, and the data we get is scary, and then people react to that, and then the next data isn't scary, so people overreact to that. But we're doing the best we can with the information we have, and that's the reality. Okay, significant figures, we talked about those before a little bit. All the digits we record in a measurement reliably. So can we count on these numbers? So when you're reading a temperature, which we've been doing, right? And the temperature, it goes from 20 to 30, 20 to 40, right? When we're looking in here, you would record the second digit as an estimate. Why? Well, this doesn't match that. Right, so this is 20 to 30, so we only have, what? We guessed 20 point, yeah, we can't even guess. We have to guess this digit. That's just bad. On this thermometer, right, we can guess this digit, all right? Because you're guessing that, because it's only labeled in 5s. This one's only labeled in 10s, so you're always guessing this digit. Over here, right, when we're reading this device, right, our graduated cylinder that goes in tenths, right, 4.10, we're going to guess 4.100 or something. This one's nice. Let's see. Here we have 4, 1, 2, 3, 4, 5, and then it's in between 5 and 6, so we're going to guess 5.5, right? 5.5, okay? 4.55. If we come over here to this milliliter thing, it's 100 milliliters difference, right? In between these two. And what's the break there? Boy, that's hard to see. Looks like tenths, right? So we're at 10, 20, 30, 40 and a half, so 640, and you're guessing this digit, right? All right, make sense? Then our conversions, right? 76 degrees, where is it? It's on our conversion sheet, because this is this is the slide you're supposed to fill in, and I don't have the slides today for some reason. I'm not sure why. It doesn't make any sense on this computer and on that computer. But how do we report that once we make a conversion, right? If we look at 76 degrees, right, that means we can go plus or minus 1 degree, because we look at the last digit, and that is the digit we use to make the difference. If we have 76.00 degrees, now we're looking at 0.01 difference, right? It could either be 76.01 or 75.99. You guys see that? That's the real issue here. So any measured quantity is considered uncertain, its last or smallest digit. So whatever number you write, that last digit is where the uncertainty is. So if I want to impress someone with my weight scientifically, right, I would say, oh, I weigh 218 pounds. But if I was going to be exact, and then that would be either 219 or 217, but I could say 218.00. Now I can only be 218.01 or 217.99, right? And that's all we're talking about. Definition: the number of meaningful digits is in a measured or calculated quantity. Calculation is no more precise than the least precise measurement used in it, and that's where we get the numbers when we do our rounding and significance, right? The smallest amount of significant figures determines how many significant figures we can use. So even if we have a giant number with lots of significant figures, we cannot use it if we have a number that only has one significant figure, because we're guessing about the numbers for the other one. And what are the rules? The rules for determining significant figures. All non-zero numbers are significant. So 138 has how many significant figures? 3, very good. 25.327 has 5. And then if we go to zeros, they can be a little bit tricky, but most of us can get this no problem. Zeros between non-zero digits are significant. So example, 23,005 has, yeah, all the figures are significant. Leading zeros, so numbers on the left end of the number, or before the digits, are not significant. They are just placeholders, and that's why knowing how to go from decimal to scientific notation is important, because if you write the number in scientific notation without the zeros, they're not significant. So 0.0036 has 2. 0.0433 has 3. All right. Rule 4, trailing zeros are significant if there's a decimal. So if we have a decimal, you count the zeros on the end. For example, 2139.010 has
7.
Yes, good. And 5,900.00 has
6.
very good. If a decimal isn't shown, ambiguity should be removed by using scientific notation. 1,500 is ambiguous, but 1.5 times 10 to the 3 has 2 significant figures. 1.50 times 10 to the 3 has 3, exactly. And 1.500 times 10 to the 3 has, good. The pre-exponential term in scientific notation always shows the correct number of significant figures. Now, what are exact numbers? This leads to debate among all kinds of scientists. However, integers and defined numbers have infinite significant figures, as many as needed. So where's the problem come in? Everybody knows what integers are, but defined numbers, right, that's where it gets interesting. So pi, 100 centimeters per meter, simple fractions. So we're not really saying they have infinite significant figures. What we're saying is they're exact, so it doesn't matter. There's no discrepancy. No matter how often you use it, it's always going to be that number, and so it's not going to figure into our calculations. Really what we're talking about is measured numbers, right? So don't throw away any significant figures. And the best way to do that is to carry all the figures with you while you're doing a problem until the very end. And that helps us define what we're doing. So in calculations, remember we did this on the board yesterday. 3.12.4 plus 4.1397 is going to end up being 3.1 or 316.5 5, and we look at the 3, and it's less than 5, so we don't round. So how many significant figures? 4. Okay. 1 past a decimal. So addition, subtraction, we always look at the numbers when we compare them to a decimal. Multiplication, uh-oh. How many are we gonna have here?
5, no. So the ours is the smallest.
2?
1.
1.
Really?
1. Yeah, 1, right? So it's gonna be 328, or 32, yeah. 328, 329, yeah. But you're only gonna use the 3, so you'd write 300, or 3 times 10,
10 to the
2. Adding and subtracting significant figures, let's look again. A sum or a difference can have no more decimal places than the number with the least digits to the right of the decimal. So in this example, right, it stops here, right, at 91, right? But now you're gonna look at that 7 and round up, right?
92.
And then this one, we stop right here, right? 2 digits past the decimal. So again, 125.04 becomes our answer. We look at the 1 for rounding. It's less than 5, so we don't round up, and it stays exactly where it is. Multiplying and dividing significant figures, a product or a quotient can have no more significant figures than the number with the least number of sig figs. So we have oh, is that a decimal? No, it's not, right? 14,000 plus 5 times 2 to the 5 times 5 times 5, thank you, times 5.23. Wow, got stuck in a rut there. It's like a broken record. So 14,000 has how many significant figures?
2.
Okay, so our answer will have
2.
2. Very good. So 842.13 divided by 40.4. 842.13 has 5. 40.4 has 3. So our answer will have 3. Right? Simple stuff. We got this. So when you start doing this with problems, don't make it harder than it is, right? Count your significant figures in the problem, and the smallest one you report. Okay. If the last digit is less than 5, drop it. Oh, this is rounding. If the last digit is more than 5, drop it and add 1 to the remaining digit before it. If the last digit is exactly 5, drop it. If the digit is even, add 1 if it is odd. Just to,
What?
yeah, you don't have to do that.
Yeah. 5 or more will go up.
5 or more go up. Just make it simple. There is some math theory behind this, but
I've never heard that.
as long as you do it the same way. This is one of those conventions, right? Whoever wrote the book had that convention. Okay, so let's round off the following numbers to 4 sig figs. 14.363 rounds to
14.36.
good. Anybody not see that? Okay, 14.365.
14.37.
Okay, 14.365.
Same thing.
Same thing. Because we're rounding at the 6, right? And we're not going to do that next part because it's the same thing. Multiple step calculation. Retain all digits till the end of the calculation. And that's the important part, right? Don't throw things away. Don't so many people do this, right? You're given a number like, hardly have any room. 5.432, right? And you say, oh, I don't care, 5.4. It's not 5.4. Okay, it's 5.432. We need these sig figs, right? Because why? Because this is just 2 little digits, and we're not gonna be able to. We're off by 1/10 already. Here we're off by 1,000, right? I'd rather be on by 1,000. Right? If I'm only off by 1,000th, I'm doing pretty good. And our scale, right, Our balance goes to this number, which is a 10,000. Now, we're talking about a very small amount of mass. I'd rather be off by that much than be off by 5.5 or 5.3, right? And you can't even see this, but 4.4321 or 5.43219, that range is much more preferable to me for anything, right? And especially if I'm dealing with things that are 10 to the 19. I don't want to be off by a tenth when it's 10 to the 19. Right? 10 to the minus 19. Or 10 to the minus 9, like a nanometer. I don't want to be off by a tenth if I'm doing things with nanometers because I don't even know what the nanometer measurement is. If I'm doing things with microliters, I don't want to be off by a tenth of a liter, right? Because now I'm not even doing, why did I even do the calculation, right? And then if I'm just that sloppy, right? Like that first student, if you're sloppy like that, when you're dealing with a human being and their condition, it's gonna be horrible for that human being, right? Fine for you, I mean, you're the sloppy one. But then it's also gonna be bad for the people who thought they'd put you in charge of someone because they're gonna be liable for the sloppiness. So when we're doing labs, it's not so much that I demand it, because I don't. It's that you need to start demanding it of yourself, right? And there are certain instructors that love to tell you, you need to do it this way, and then they'll stand there and tell you to do it, and a lot of people really like that. Myself, it just makes me want to backhand it, and that's not good. I know, violence is never the answer, but that's my own mental illness. But you don't want to have that mental illness. So you respond, I like to do it with, you know what, this is the way we should do it. If you want to do this job, if you want to be in this science field, if you want to move forward, you should probably pay more attention to detail. That's my only warning. Now there are other people who say, no, that's unacceptable, no points. I want you trying, and I want you moving forward. Because there's all kinds of good people out there who have the right emotional makeup to take care of people, just need to learn the discipline to do it. And the thing about emotional people is generally, if you're mean to them, they give up. And then you lose the kind of person you need to take care of people, and you're left with people who like to make people follow the rules. Here's something. If you are so mentally ill, you won't take care of yourself, what are the chances you're going to follow the rules they give you to take care of yourself? Okay, this is the kind of science logic that has to be answered. I'm not saying right or wrong. I'm just saying, if you can't figure out how to stay indoors and stay clean and healthy, how is someone telling you to stay indoors and stay clean and healthy going to help you? And that's one of the societal problems. A lot of the people who like to help have a lot of rules. They say, if you want help, you're going to do this. But if you can't do that, if you could do that, why would you even need their help? They're just questions. I don't have any, I'm not. Anyway. So that's why we need to be careful with our units. That's my bottom line is significant figures matter. They really, really, really matter. And that's why we keep bounding them into you. Because if you're off by, if you want a gallon of gas and you know that you've got a gallon almost to the, to the little drop, you're gonna be a lot happier than if it's close. And then you get halfway to where you're going and you're out of gas again. It used to happen to me all the time when I was a kid. But I could only afford half as much gas as I needed to get to where I wanted to go. Okay, so enough of those stories.
Wait, we missed the other.
This one, we didn't do this?
No.
Oh, okay, yeah. Retain all digits till the end because you don't want to shortchange the calculation. You don't want to be off at the end of the calculation. This happens a lot in our lab when we go to read the scale, right? You record all the digits on the scale because we need them all in order to make our calculations come out correctly. So if only addition and subtraction are involved, use the addition and subtraction round-off rule. Okay, which is what? We just went over it.
5 or more go up.
Okay. And if any multiplication is involved, use multiplication, division, round off rule for that part of the calculation and keep track of the number of significant figures to use in the next step. So with the addition subtraction, we're talking about how many places past the decimal, right? One recommendation is that you underline the least significant digit in each step of your calculator. We did that in lab when we were talking about how to deal with that one weird number that we had, right? Examples. 12,415 plus 12.14 times 17.2. Equals what it does, so how many significant figures?
Are you saying that instead of carrying it all the way through, you want us to do like what's in the parentheses and figure out the sig figs there first before moving on to timesing? Is that
Yeah,
what-
you figure out the sig figs, right? No, you just figure it out, you don't do anything about it yet, right? You do the whole calculation, and then you figure out the significant figures.
Based off of the original numbers?
Right.
Okay. I was reading this as like, and then keep track of that as you go, like each time, like. the original-
Well, you keep track of how many you need at the end, and that's why they say underline it in the first step. So in our first step, we have 0.14, right? So when we do that addition, we're gonna drop the 5 at the end, right? Because we would have nothing there, so they wouldn't even count, right? So you have none past there, you just have the 12, you have, right, it starts, all these are significant, right? So 1, let's just do that. Not with this one.
So you don't go off of the 3 significant figures from 17.2 because it's not in the.
Yes, you do. That's the whole point. The whole point is, if you keep track of everybody's significant figures, right? But at the end, you go to the smallest one. But if this number, this first number actually had a decimal instead of was just 12,415, right? And then the next number is 12.14. So for this number, it would only be 12,427, right? If we were doing the multiplication, the addition only. If we were only doing this step, this would be our number of significant figures right here, right? Because we're adding them together. But then we're doing the next step, which is, right? So once we've done this, but we carry this through, right? It's still there in our calculator. We only drop it when we report the answer. So the answer will have 3 significant figures, and it'll be 2,000 or 213,000.
Wouldn't the number of significant
yes, 40.
figures that you carried over affect what your number would be when you times it by 12.7?
Right, it has an influence, but we're not counting that influence. Because you can see this is even farther that way. What we've dropped has no influence on those 3 numbers.
Oh, see, I thought you dropped the 14.
No.
Okay.
Well, yeah, I dropped this part. That's what if I was just doing the first step and reporting the first step as an individual equation, I would drop those 2. Because there's no decimal here. But that doesn't mean there's only 2 significant figures, because it's addition. Significant figures in addition come from what's on the other side. So these 2 numbers are equally valid. You're not only gonna report 12,000. But when we get done doing the math, now we're putting in the 3. Now you look like I confused you, even though you knew what was going on before. So this one has 3 significant figures. You guys with me on that?
Mm-hmm.
All right. So look at the next one. So if the next portion, we have a similar situation. We have a 15,213 addition and then a subtraction. So we have to line all these up. But what happens is, since 15,213 doesn't have a decimal, all the numbers on the other side of the decimal don't count. So, when you line this up, and obviously this is important to us, or I wouldn't be spending all day on it.
2, 3. 15,213.
And these are all added.
Then subtracted by 0.402.
Okay, so when we do this, all those drop and all these stay. You still do the math as if they're there, but when we go to report the answer,
So then do you only use one significant figure, since the 7.0023 is the
No, it's
smallest?
addition and
no,
subtraction.
it's addition and subtraction, so everything to this side not. Right? All these numbers are significant.
Okay. I thought you used the smallest one though. Like
Yeah.
you,
For
That's
addition.
Multiplication and division.
okay,
For this, you use the decimal point, and so let's say this had a 1 here.
Yeah.
Then we'd use all the ones here. Right? It's not one, this number would have one significant figure, but this one would have 1, 2, 3, 4, 5, 6. But you don't count it as the smallest one, because all these numbers in the rule book have a significant influence.
So then how would you write these
Right.
answer?
So the answer then would be,
Significant.
right, would be to here, but that would make it a 5.
Okay, so you're just entirely, okay.
Because there's no significant figures on the opposite side of the decimal. Are you with me?
Though I thought you,
Right? Because this says, this one has no significant numbers on the other side of the decimal, so therefore,
Oh.
you can't go past,
I missed that didn't have a decimal point. Okay, I'm with you, good.
so if that 15,213 wasn't in that equation.
That makes it,
then-
there's 0 significant figures past the decimal point, yeah.
so, yeah. So this is gone, now, that's your question, right?
Yeah, now it, would that be 2 or 4 significant?
1, 2, 3 past the decimal, 1, 2, 3 past the decimal, 1, 2, 3 past the decimal. Yeah. That would, so then we'd report
2.
to here,
Okay,
1, 2, 3.
perfect.
Yeah? That was a great question. Did you guys see that? So, and that's a good way to do it. How many significant figures would there be if we took this away? Well, still this, it was still nothing past the decimal. If we took this away, nothing past the decimal. But the minute we take this away, now we're including the numbers on the other side of the decimal as part of the answer. Fantastic.
Now for that 7.0023, you wouldn't count those zeros even though they're,
Yes, you do.
you do, so that would be 4 significant.
Yeah, that would have 4 significant figures
Figures
past the
past
decimal,
the decimal.
5
Okay,
including,
got it.
including the 7.
Got it,
Yeah?
got it.
So, this is what saves you, right? Because in 120, I didn't care how you reported significant figures. I wanted you to, but now I really care. So it's gonna cost you if you don't get them right. It's just a point. All right.
Why
The
is
ne-
it after you take out the 15,213, why is it that you have to count the numbers after the decimal?
Okay, because when we line up with significant figures and decimal points, right, that's how, so let's do it again. If we have 15.213, right? This has 5 significant figures, 3 of them are past the decimal point, right? Okay, when we do addition, we keep track of everything on the other side of the decimal point. This has 7.0023. So this has 5 significant figures, but 4 of them are after the decimal point. When we add these 2 numbers together,
Stop there.
you stop here because this number doesn't have anything to contribute to the end. So this would be 22.215 And the 3 would be there, but we get rid of it because it doesn't make this number go up or down. Then we do the last number. And again, we're keeping this here because we haven't finished yet. So we have a 3, a 3, a 1, a 21, and an 8.
And we go by what's based off of 15.213 because that's the smallest number of significant figures past the decimal point, right?
Correct. Exactly. So our answer then is 21.813 because these numbers are significant in addition and subtraction.
And if that 3 on the end was a 5, would you just leave it as a 3?
Well, if you're the kind of person who rounds it up, you'd round up, and if you were the kind of person that doesn't,
What do you
you'd
want
leave
us
it.
to do?
If you had a 6,
You round it up, that'd be a 4.
that'd
I
be a
would
4.
round it up, but with a 5, what do you want us to do?
I round it up.
Consistently.
Yeah.
Whatever you do consistently. Or you can do it up one time, down the other. I don't really,
Okay.
as long, or you can leave it alone, right? Because rounding down is leaving it alone. So leave it alone or round it. Or you can follow that other rule if that makes you
That was
more
about
comfortable.
$5.
So let's look at the last one here. 12,000, so we're gonna do what's in parentheses first, right? PAMDOS or whatever it's called. No, that was something else. PEM, yeah, PEM, not PAM. Right? So inside the brackets, we have how many, so this is gonna be an easy one, right? Because we have to go back to what? One significant figure.
Yeah.
Is the division. So all the other stuff doesn't matter. Because our division says, once we do division, at the very end, when we get done fiddling around with all this nonsense, that 6 right there tells us what we're gonna report. Right? So really, you don't even have, I shouldn't say it this way, but really you don't even have to keep track of anything because once you have your division, you got one significant figure. And so at the end, when you get to your final answer, you're gonna report one significant figure. All right. So now we have significant figures. We have measurements. We're almost ready to do more, right? And what do we mean by more? It means changing one kind of unit into another, dimensional analysis. All measured quantities have units. Conversion factors are known. 1 kilogram equals 2.205 pounds. 1 meter equals 39.37 inches, and I know I haven't posted the conversion factors up yet, and I haven't passed them out yet, but I will. And fact 3, conversion ratios are all unity. This is the important one. 1 kilogram over 2.205 pounds, or 2.205 pounds over 1 kilogram. You can use them interchangeably, right? Wherever you need the units to be, it equals 1, right? Because that's one of those conversions. 12 inches equals 1 foot equals 1. 453.6 grams over 1 pound equals 1, right? But also the inverse is true. Okay. That's what allows us to do dimensional analysis. How many units of A are in units of H? That's the basic idea. Must be the same type of quantity, length, time, weight, etc. So all our measurements must match in units. The units have to match. So convert value in units A into values in units H. Use conversion ratios to change the desired units by canceling unwanted units. So A, cancel. We're gonna go to B, then go to C, so we cancel B. We're gonna go to D, so we cancel C. Right, you see that? Cross out, cross out, cross out, cross out, cross out, cross out. All the way, and etc. So you can do this indefinitely, right? To get from one point to another, and that's what we take advantage of. A lot of people like to follow a roadmap. I kind of don't. but I'm teaching that you do. So what does that mean, the roadmap? How do we get from one set of units to another, and what are the conversions? And they like to do that before. I like to let the units convert themselves. right? I'm gonna take a unit and I'm gonna make it into another unit. And then that's gonna tell me I've got that relationship. Where else do I have that relationship in the problem? Let's make that a unit. So which conversion factors will get me from units of A to units of C, and from units of B to units of D, right? That's what we wanna know. And that's the basis of these type of problems. So you arrange conversion factors so the starting unit cancels. The starting unit is always on the bottom of the first conversion factor, right? So we have our given units, whether they be, let's just say they're seconds. So seconds here, seconds here. And let's say the new unit is a minute. So seconds, seconds, minutes. Minutes, hours. Hours, mega hours. Okay? So that's the way the change goes. One step at a time. And this is the ones where I want you to show your work. Why? Not for me, for you. Because if you just go through willy-nilly and do these, which a lot of people do, and a lot of people keep it straight in their head most of the time, but every once in a while, instead of writing their final unit as time, they write it as mass or something. And this keeps you from doing that. And it allows me to give you points every step of the way, which is also how you get through a class, at least in my world. Convert 346 centimeters to meters. So you choose a conversion factor. 1 meter equals 100 centimeters. Okay, right or wrong? There's a wrong way? I don't know. I mean, we're not showing that. The right way, right, is to take, and let's just do that over here again. Is this showing up at all? Can you guys see when I write over here?
It's on the right side, see at least.
346 centimeters, and we want to go to meters, right? So centimeters go on the bottom. I don't even have to know what I'm doing. The very first thing I do is I take the units I want to get rid of and put them on the bottom. And then the units I want go on top, meters. Okay, so centimeters smaller, so if I want to do 1 meter, I have to do a whole bunch of small ones to make one big one. So 100 centimeters on the bottom. And 346 divided by that is 346, right? 0.346 meters? No. Bad Jim.
3.46.
Yeah, bad Jim. I had myself convinced. 3.46 meters. Is that right? That's not right, is it?
Yeah, that's right.
3.46? Yeah, because 46 is half of 100, right? Okay, so 3 of these go in there. Yeah, that makes sense. Okay, whew. Like, you know, that's part of it. You can convince yourself of anything if you argue long enough with yourself. All right, so.
The other way could have been your wrong way.
See, that's why we do the wrong way. You don't do the math. All right, so systematic approach. Sort the information from the problem. So that's what I like to do. You get a problem and you just write down the information. You don't read it because you just want the information first. Identify the given quantity in units. I like to write the units with a question mark. What am I looking to get? That's the question mark. Everything else gets the name and the units written down. That way, even if I don't do anything with the information, I've taken it out of the problem and I put it there and that's worth points. Right? Because at least I've identified what I'm looking at. I've separated. That's the first step in doing anything. Like, okay, there's items. Identify the items on this table. Well, if I just leave the items there and go over here and go, I don't know what those were. That's different than if I say, okay, there's a lab notebook, there's some napkins, there's a green pen and a black pen, and there's this backpack with sunglasses on it, right? Now I've identified at least what was on the table. I may not have solved what I want to do with it, but I've identified that I recognize that there's a problem, right? Which is always the first step to solving a problem, recognizing there is a problem. You'll hear that throughout your life. Design a strategy to solve the problem, okay? So now the problem is, I moved everything from one table to another. How do I get it back? Do I enlist help from the students? Do I do it myself? Do I just leave it there for the janitor to do? Which is why we clean up our bench, by the way. We don't leave things for other people to do. And I took a picture of somebody who left their burette set up last week when they left. All right, so each step involves a conversion factor and equation. Sometimes we want to work backwards. Sometimes on a long problem, you go, oh, I know this part. And so you put that part in and then figure out how to get there. Check your answers. This is the part that I love. That's what I was doing here, right? I was like, is it 3.46, 0.346? What makes sense there? Oh yeah, 100 goes into 346 more than once. So it's gotta be bigger than 1. So my initial answer was wrong because it didn't make sense. You can't have more than 1 and write down less than 1. And that's kind of one of those, wow, even if I get it wrong, I could write underneath it, I know this answer doesn't make sense because I checked it and I know it should be bigger, I just don't have time to fix it. That lets me know that you're using a check to the answers that you get, which is part of problem solving, right? One of the things that happened during COVID is we started throwing answers at problems without checking to see if they made sense, right? And that cost a whole bunch of people in New York their lives, a bunch of older folks, and that's unfortunate. They were trying to do the right thing by isolating them. They just happened to isolate them with the most sensitive population. So, but if they would have checked that and said, wow, the old people are the most sensitive, we shouldn't isolate people with them, then they probably wouldn't have done that. And they're probably gonna end up liable, or at least I hope so. Check your answer, make sure units cancel, make sure it's reasonable. Units raised to powers. General rule, if a unit is raised to a power, oh, we're done. We're gonna stop right there. Held you long.